So this is not related to what I talked about yesterday, so this is a new topic. This is on homogenization of reaction-diffusion systems. This is a joint work with Grégoire Allaire from École Polytechnique and Laurent Devillette from Paris Diderot. So the talk I have organized as follows. I will not do the homogenization step because you're all familiar with that. And so I'll give some technical details before one performs homogenization. Okay, and this is a nonlinear reaction diffusion system. So as we go along, I will highlight the main difficulties. Okay. So this is the setting. Okay, believe me, so the model which we study, it has many applications. I will not dwell into that. I'll straight away give you the mathematical model and go on with that. So this is a reaction diffusion system. So we are not trying to optimize regularity assumptions on the domains, okay? It can be as regular as we want. So there is some open bounded domain omega, and it's filled with solvent. And in it, you have some number of chemical species, okay? So take L of them, L number of them. So each of those chemical species, they have their own concentrations, okay? U1 up to UL. So UIs, they are just scalar valued functions. So if you want to know what's the meaning of this concentration, so UI, so say this is function of space, okay? And if you integrate over some domain, this will give you the amount of that species, say AI, in that region B, okay? That's the way you should understand, and these are all non-negative functions. So there are L unknowns, these UIs are the unknowns, and these are the independent variables. So these UIs, the concentrations, are functions of time variable and the spatial variable. So we need to write L equations because you have L unknowns for these concentrations UIs, okay? So the underlying modeling is these chemical species, AIs, they are involved in some chemical reactions, and they are, at the same time, they are diffusing in your spatial region, okay? So first thing, the time derivative of your ith concentration, it's equal to some rate function, okay? So this rate function you will write, so we will fill in the details as we go along. So this rate function, it's the rate of change of your concentration because of the chemical reaction it's undergoing, okay? So this Ri, so we'll give the expression for this Ri later on. So this will take care of the chemistry involved, and they are diffusing in your spatial domain, and that is modeled by, a second order elliptic equation, elliptic part, okay, sorry. Somebody's calling. I'll keep it here. So they are diffusing. So that looks like divergence of something times the gradient of UI. Yes? No, I mean, we are only interested in reversible chemistry. Okay, thank you. Yeah. So we will just model reversible chemistry. Okay? I'll get to what this reversible chemistry is later on. Okay? So now, what is this diffusion coefficient? First of all, we scale the problem. We want to study something called long-time large-scale behavior. So we scale the spatial domain and the time variable. So you go from t to epsilon square t and x to epsilon x, okay? So it's in order for this new variable to be order 1, your little t should be of order epsilon minus 2. That's why it's called large time. And this is called parabolic scaling in time and space, okay? Parabolic scaling. Say, if you write the ET equation in these variables and do this change, parabolic scaling, in the new variables, you will not pick any epsilons, okay? Heat equation is invariant under this. But if you have a right-hand side, it will get a 1 over epsilon because Okay? That's not scale. That's, there are no derivatives here. And this is the type of diffusion coefficients which we are considering. Okay? So each of the coefficients, they come with their own diffusion coefficients. Okay? Each of the concentrations. If these DIs are the same, the problem is very trivial. Okay? If the diffusion coefficients are different, the story is very different, as you will see. Okay? Now, the usual assumptions on this matrix D. This is matrix valued, and this being a homogenization conference, it's going to oscillate. And you are going to assume the usual ellipticity assumption, and it's bounded. Okay? And these DIs, the little DIs, these are some functions which are not the same for everybody. Okay? At least for two species, they are different. And this is a parabolic problem with some nonlinearity. So you give it some initial data and some boundary data, say no flux boundary conditions at the boundary. So that's fine. This one, yeah, I mean, you find a uniform lambda. We are not doing any degeneracy, as you will see. Do you want that lambda to be the no, okay. They need not be. Yeah, you can always take the minimum of the two. Yes. No. yes. So, yes. Okay. So this is the equation. Okay, it's similar to what was presented this morning and also earlier. A parabolic equation, and there is this 1 over epsilon square term. Okay, just keep this in mind. This is because of the scaling. Of course, you want to now let epsilon go to 0 and find the equations. So this is a system of equations. There are L such equations. Okay, this is for each I. And the initial data which we take, it's not going to have any oscillations. It's the fixed data for everybody. Okay, I mean with the epsilons. It doesn't depend on epsilon. Okay, so now for the reversible chemistry, this right-hand side we have. So these chemical species, they are involved in a reaction like this, okay? So all of them, they combine together to give something nice. There is some chemistry happening. And these alpha i's and beta i's, they could be 0, okay? So they are just some numbers. They are usually called stoichiometric coefficients in chemistry. And the number, this kappa F and kappa B, they are called reaction rates. Okay, these are the rates at which the chemical reaction happens. Okay, so this is a typical reversible chemistry. There is only single reaction. So this is another point. There's a single reaction, but there are L species involved in this single reaction. Okay, so when you have a reversible chemistry like this, the rate function, this comes from law of mass action. You write the rate function. This was the Ri which was used in the equation. And this comes from law of mass action, which says that the rate of change of your ith concentration or the species, it is given by this as soon as they are involved in this reversible chemical reaction. Okay? It may look horrible because of the various alpha i's and beta i's, but this is the rate function. Okay? For now, you just keep in mind that the Ri's, they are polynomials in the Ui's, okay? From whatever chemical reaction we are writing, they are just polynomial functions of Ui. Okay, so I'll give some examples, okay? So let's say we have 3 species, okay? L is equal to 3, and we choose these alpha i's. Alpha 1 and alpha 2 are 1, and alpha 3 is 0. And beta 1, beta 2 are 0, and beta 3 is 1. So this reversible chemistry looks like this. Okay, and we are going to also, this you can always do. You can factor out some kappa such that kappa F is kappa and kappa, the backward rate is some kappa times gamma. Okay, now by law of mass action, what is this rate functions? The 2 rate functions for the first and second species, they are the same because there's no difference between them in terms of the reaction. This is the rate function for both of them. And for the third rate function is this one. Okay? I just want you to use this formula, substitute what alpha i's are, and just write them down. Okay? Now, I want you to make one observation. When you sum R1 and R3, they are 0. The same is true for R2 and R3. Okay? We are going to exploit this. There's some cancellations are involved. Let me give one more example. This is the 2 species case. There are only 2 species now, L is equal to 2, and these are the rate functions. Okay? Again, if you take a linear combination of them, they are vanishing, the sum of them. Okay? Okay, it may look like I'm just giving some examples, but this is the 4 species one with this particular choices of alpha i's. And for simplicity, I have just taken both the rate functions to be, the forward and backward rates to be 1, and the rate functions look like this. And here you have these cancellations, the following cancellations. If you add R1 to R2 or R4, they are all 0. Okay, the sum equals to 0. Okay. So, I will present most of the computations for this 3 species case, okay? Because whatever difficulties we face here are present in most of these equations. Okay, when this is staring at you, let me give some references. I will not talk about existence theories. I'll just give some references, okay? To your surprise, okay, let me just keep this rate function here. I'll give a couple of references which I couldn't type onto the file. There are works in the literature where they take these reaction diffusion systems and take the same diffusivity for everybody and study the nonlinear reaction diffusion systems. Life is easier there, okay? When the diffusivities are different for each of the species, it's very hard. And if such questions interest you, I welcome you to consult this review paper, which was written by Michel Pierre in the year 2010. This is about some of the existence and uniqueness results for without the epsilon, okay? So just this parabolic reaction diffusion systems with reaction terms which come out of this reversible chemistry, okay? And so this is a survey paper, very nicely written. Then, okay, one question which pops to mind is, okay, are there any global existence results, global in time existence results for these equations? Very recently, there was a work by Julian Fischer. It was published in ARMA in the year 2015 for reaction terms which look like this, okay? He proved something called global existence, global in time, existence of some solutions which are called renormalized solutions. Okay? So, to show global in time existence and uniqueness of partial parabolic problems with these reaction rates, it's a big open problem. It's not addressed because he just proves existence of renormalized solutions which are global in time for these rate functions. And there is no uniqueness in general. Then you might have wondered why I'm giving this particular example of 4 species. This is a very popular model which is studied in this field. And last year, Philippe Souple, he gave global in time existence of solutions and uniqueness of solutions to this 4-system model. This is Journal of Evolution Equations, 2018. This is for the 4-species model with that reaction rate. There's no epsilon, okay? So that's for a fixed epsilon, think of that. This is about global in time existence. So using some very hard machinery of the Georgi Nash Moser There is also this work of Thierry Goudon and Alexei Wasser from 2010, which again studied this 4-species model. They study some regularity theory, okay? So if any of you are interested, I welcome you to refer to these, okay? And so these are some of the existence works on these models. So you can think, okay, fix an epsilon, you study the existence results and do that. So in this talk, I'll just talk about this 3-species model, okay, with this quadratic nonlinearity, okay? And we want to pass to the limit when epsilon goes to 0 here. So there are 3 equations in this system. So there is 0 Neumann boundary condition, there is 0 flux, and initial data. Initial data doesn't depend on epsilon, okay? So let me make one remark about these reaction rates. Just consider, from now onwards, you just think of the 3-species model, okay? So this is the reaction rate, right? So I just multiply the reaction rate by the logarithm of that concentration, okay? And the third one by the logarithm of this gamma times its concentration. And I sum them, sum those products. You see, you get this. Because of the monotonicity property of logarithm, you get a sign for this fellow, okay? So suppose you have no diffusion. So you are just studying this ODE coming from these reaction rates. If you're studying this ODE system, okay, this, if you just do the same calculation with the logarithms, you get that this function, you have to add a constant because this graph is just below the x-axis for a while, and then so you just add a constant to make it, okay? So you find that the d by dt of this function is as a sign, okay? So this is like a Lyapunov functional for this, okay? So, and you can think of this as the entropy associated with this ODE system with no diffusion, okay? So there is this entropy dissipation, okay? So just keep this in mind. There is some functional associated which you can define on the solutions of this system which decays with time, okay? Okay. So now, what's the typical strategy for homogenization? I am sure you all are aware of this, having gone through the training here. So let me just give a quick overview. So this is our evolution equation. We want to pass to the limit here, okay? We want to find whether this ui epsilons, they converge to something, and is there a homogenized equation for this fellow? Okay, forget this. So, and we want to characterize this ui star, right? So in a linear setting, what do people usually do? You look for uniform bounds on the solutions, ui epsilon. When I say uniform, you are looking for some bounds in these spaces, LP in time, W1P in space, for some P, okay, which is dictated by your problem, which is uniform in this epsilon, okay? In linear problems, that's the usual strategy, okay? You look for uniform bounds, and then you get weak convergence, and that's enough, actually. You can pass to the limits and get the characterization of ui star, and that's it, okay? When it comes to nonlinear problems, you want to show some kind of strong compactness in LP. And that P is again dictated by the problem you're working, okay? So you want to get strong compactness. Omega T, this is the standard notation that 0T cross omega. This is the parabolic cylinder, okay? So this is what you need to do. If you are in a nonlinear setting, you need to get some strong compactness in some LP for your solutions. And that's what this is, okay? And that's not something specific to systems or anything. Even if you're doing scalar nonlinear equations, this is what you do, okay? So let me tell you let me write down the equation just for our reference. dt ui epsilon minus divergence of di of x d of x over epsilon gradient ui epsilon is equal to 1 over epsilon square ri u epsilon. Okay? And there are 3 such equations. I mean, for the third one, the R3 has a different sign, and when you add R1 and R3, it equals to 0. So what's the battle plan? First, we will show that if you start with non-negative initial data, your solutions stay non-negative. And that's very important because you're trying to address these as concentrations of your chemical species, and there's no meaning of having negative concentrations. So if you start with non-negative data, you should stay non-negative. So that's something we will prove. Then we prove, I showed you this entropy calculations. Using a similar calculations with the logarithms, you can show that the L2 norm of the gradient of the square root of ui epsilons, okay? It's bounded in uniformly. All these constants, whenever C appears, it's always uniform in epsilon, okay? This is our second step, okay, which I call entropy inequality. Then we do some energy estimate to show that you have an L2 uniform estimate on the concentrations, okay? By combining the entropy and energy, this energy estimate, both of them, we will show, you see, this was the thing in the linear setting, right? We had to show that LP in time, W1P in space estimates for the concentrations, and that P happens to be 4/3. Okay, this is what we will gather from step 2 and step 3. We will deduce that ui epsilons are uniformly bounded in L 4/3 in time, W1 4/3 in space. Okay, so this is, let's say, the linear part. Okay, this is what you would do for a linear problem to get LP W1P estimates. Okay, this is what we do. Next, this second section will be on the nonlinearity part. Okay. Rather than showing that each of the UIs are relatively compact in some LP, we take a little detour. We will show that the sums of the concentration, particularly U1 epsilon plus U3 epsilon, that is relatively compact in L 4/3. That's what we will show. And similarly, U2 epsilon plus U3 epsilon. Okay? So this is what we will show first. Next, using this information from step 1, where we show the relative compactness of the sums, and combining that with the entropy inequality, which said that the gradient of the square root of ui epsilons are bounded in L2, we will get that the ui epsilons are relatively compact in L 4/3. Okay? But you have particular nonlinearities in your problem, and if you show relative compactness for some arbitrary p, it doesn't work. You need to get a relative compactness in some right exponent p. For that, you have to do one more step of parabolic duality estimate. And here we will show that the solutions ui epsilons are in L4 plus delta for some positive delta. Okay? Then I hope you all are aware of interpolation inequalities in LP. So you have shown that UIs are strongly converging in some LP space, and you have shown that they are also uniformly bounded in some larger LP space. Okay? Then they will be relatively compact everywhere in between. Okay? So you combine this information you have that UIs are relatively compact in this, you have a uniform bound, so you will be relatively compact in L4. Actually, for this particular problem, you need relative compactness in L4. That's why you do the duality estimate to get 4 plus delta. It will become clear when we go along. I just wanted to list all the things we will do, and then we do step by step each one of them. Okay? And this is the interpolation thing. So, no. It comes from the fact that we have an estimate on the gradient of square root of epsilon, u epsilon. You know, in the entropy estimate, usually for these parabolic problems, you get estimate on the gradient of u epsilon, right? But this entropy estimate simply gives this, and that's the best you can do. And once you have this, this is from the entropy estimate. You get this, and this is typical of these nonlinear problems. You always get estimate on the gradient of the square root of u epsilons. And then it's manipulation with Helder inequality, you get 4/3. Okay, I'll show that step. Okay, and for those of you who don't know interpolation, the consequence of interpolation inequality just says this. if you have a strong compactness in LP, and if you have uniform bound for some Q larger than P, you have strong compactness in LR for every R between P and Q, but not Q, okay, excluding that. Okay, this is the homogenization result. I will not do the homogenization step. I'll just give you the result. I will show some of the details involved in proving those steps, which we outlined. So this is what eventually comes after you have proved the uniform estimates. You will show that the solution to that problem, ui epsilons, they strongly converge in L4 to some ui stars, which will solve this one. And in Antonio's lectures, there was this, similar thing. There was a partial differential equation, and then there was some algebraic relation was there, and there is the similar structure here. You have three unknowns, right? U1 star, U2 star, and U3 star. So there are two equations here, and there is an algebraic relation relating the two. Okay, so there are three equations, three unknowns, but that's not enough. You need to actually show that it is well posed. And so if you observe here, if you substitute this algebraic relation into the PDEs, you'll get something called a cross-diffusion equation. The diffusion part of your UIs are related to the other concentrations in your system. That's the cross-diffusion models. And these BIs here, they are the classical homogenized coefficients. There's nothing special about them. And okay, so this I told. The limit problem, it couples parabolic problems with algebraic expressions. And then if you substitute this algebraic expression into these partial differential equations, you get something called cross-diffusion models. And I'll give one more reference here from where you can deduce that this homogenized model is well posed, global in time, okay? So this is for cross-diffusion models. This is Didier Bottet, Michel Pierre, and Guillaume Roland. This was published in Communications in PDEs in 2015. This is a very hot topic in PDEs to study these reaction diffusion systems. And some of these things can be a starting point to get to know what's happening. Okay, this is our homogenization result. As I said, I'll not be proving this result. I'll just show you some of the calculations involved in those 8 steps, which I mentioned earlier, okay? So let's go to this linear part, which involved getting uniform estimates in L4 thirds and W1 4 third. So the step 1 was to show that if you start with non-negative initial data, you stay non-negative, right? And okay, this is what it says. So you start with non-negative initial data, you stay non-negative. So this is a standard trick. It usually works, okay? So this is like an energy method. You take your differential equation and you multiply by the negative part of your concentration, ui epsilon, which is simply minimum of this function or 0, okay? This is the negative part of your function, and you multiply. And it so happens that the rate functions which come from this reversible chemistry, they are well adapted to getting a sign for this term, which when you multiply Ri by ui minus, you'll get the proper sign to conclude that your solution stays non-negative. So it's just, you multiply, integrate by parts, do the same thing, and it will always come. Okay? The main part will be this, the term involving this, but if you observe carefully, it will be fine. Okay? So this trick usually works for most of the parabolic problems. Okay? When you want to show non-negativity, you just multiply by the negative part and do integration by parts. Okay? So we have shown that the solution is non-negative. Now we will show this estimate. All right? The entropy inequality. That the solution to this problem for each I, the L2 norm of the gradient of the square root of that concentration is uniformly bounded. Okay? This is integral in time and space. Also, in the computation, you will gather this particular estimate. Okay? As you will see, The reason why you get this is you are using logarithm of ui's as the multipliers in your energy method. Okay, if you think how you can take, you have just shown that the concentrations are non-negative. How can you take logarithm of those non-negative functions? You're not avoided zero yet, right? So the usual trick here is to add a delta to your concentration, take the logarithm, and do the entire procedure. Then at the final step, you let delta go to zero. Okay? Then you will not lose anything, and that's how. So how do you prove this result? This is by multiplying each of the equations by logarithm of ui's. So this step I showed when I showed that entropy dissipation structure for the ODE. So you take the first equation and you multiply by logarithm of ui epsilon. The second equation by logarithm of this is u1, this is u2 epsilon. And the third equation you multiply by logarithm of gamma u3 epsilon. And you just integrate, and you get this. Okay? And because you are multiplying by logarithm of u1 epsilon, the diffusion term, when you do the integration by parts, you will get, see, gradient of u epsilon. But when the gradient hits the logarithm, you get the 1 over epsilon, 1 over u epsilon, gradient of u epsilon, isn't it? This fellow is exactly gradient of square root of u epsilon. That's why you get, right, this fellow. You forget that, I mean, because we have assumed, the nice assumptions on D and DIs, that they are elliptic. So essentially it boils down to this. And what is this product? This is exactly gradient of the square root of ui epsilons. And that's the reason why you have L2 estimate on the gradient of the square roots and not the gradient of u epsilons as you are used to, okay? So you get this. Now, what is this energy estimate? So first of all, you need to recall this. I have repeated a couple of times now, that if you add the rate function for the first and the third one, you get zero. So what you do is you take the three equations you have, you add the first and the third equation. You will lose that annoying 1 over epsilon square term because the rate functions cancel. So you essentially get a kind of parabolic equation for the sum of the concentrations. Then you have to do some, integrate in time, do integration by parts. This is the tricky bit. You have to use this fellow, d1 times u1 epsilon plus d3 times u3 epsilon as the multiplier. Okay? Otherwise, this energy method will not work. This might be the reason that this L2 estimate for these systems was known only recently. Okay? It was not proved earlier. This was proved by Michel Pierre with one of his collaborators, the L2 estimate, maybe 15 years ago for these reaction diffusion systems. And they used, once you know the solution to these problems, they look obvious, but the trick involved was to take this as the multiplier in your energy method. Okay? Okay, but in this expression, if you take this as multiplier, integrate over omega and time, then you get this L2 estimate. It's a bit lengthier computation, but the essential ideas are here. Okay? Now for the step 4, we have got the estimate on the gradient, we have got the L2 estimate on the solution, we have shown that it is non-negative. Now we have to get this LP W1P, right? So the claim is UI epsilons, they are uniformly bounded in L 4/3 in time, W1 4/3 in space. Okay. You use the information from step 2 and step 3, which says the information on the gradient of the square root of U epsilons and the L2 estimate of the solution. Now, a simple application of Helder inequality will give you that the gradient of U epsilons are in L 4/3. Okay? And here it is. You just take what you want to bound, you multiply and divide by this. These are just tricks. Once you know them, you know them. Okay? So you do this, and then you apply Helder with these exponents. You get this. And this is bounded because you have just proved L2 estimates, and this is bounded because gradient of square root of UI epsilons are bounded. Okay? So now, let me just write down while you stare at this what we have shown. So we have shown that ui epsilons are non-negative. We have shown that gradient of square root of ui epsilons are bounded in L2 of omega t. Then we have shown that ui epsilons are bounded in L2. And finally, we have shown that L4 thirds, 0t, okay? That's the 4 steps we have done for each I. There are 3 concentrations and we have shown that. Okay? If your problem were linear, this will suffice, okay? Now you can do your homogenization step. You can just pass to the limits and fine. But this is not sufficient to pass to the limit in this Ri epsilon, Riu epsilon term because they are quadratic. So you need to work a little bit. So let me go to the nonlinear part where you get relative compactness in some LP space. As I mentioned, rather than showing that each of the concentrations are relatively compact in some LP, we first show that the sums of these concentrations are relatively compact, okay? So you add the equations for 1 and the third concentration. And as I said, because R1 plus R3 is 0, you lose that 1 over epsilon square term, okay, when you add them. So what exactly you will have for the sum, okay, if you have noted this down, you will get dt u1 epsilon plus u3 epsilon, for example, minus divergence of d1 d gradient of u1 epsilon minus divergence of d3 d gradient of u3 epsilon, but the right hand side is 0. Okay? It's not of the form, okay, you cannot call u1 plus u3 as a new unknown and write it as a like dt of w minus divergence of something. You cannot write that, but you are close. Okay? You can do the usual steps to show LP compactness. And for that, I recall this Aubin-Lyon's compactness criterion. Okay? It says the following, it's quite simple. You need to have 3 Banach spaces, okay? B1, B2, B3, which are contained like this. And if you have some equation, and so some family W epsilon, if you show that W epsilons are in LP in time B1, this first Banach space, okay? And the time derivative of W epsilon are in LQ, where Q is the conjugate like this one, and it's valued in B3, the other endpoint. So you take a sequence which is valued in the first, and the time derivative of the same sequence valued in the other end, then your W epsilon will be relatively compact in LP in the middle, okay, in the B2 Banach space. So once we have written down the equation for the sums, what do? We have already shown that each of the UIs are in L4 third, W1 4 third, right? So if you sum 2 concentrations, you are still in the same space. So U1 plus U3 are in L4 third, W1 4 third. Now, because the sum is 0, once you have written this down, it's a standard trick. You multiply by test functions which are here and do the duality argument to show that the time derivative of that sum is in L4 in time W minus 1 4 in space, okay, which is the dual of W1 4 third. So you have got this. Now you do the same trick. That will, you take T is equal to 4 third, Q is equal to 4. You apply Aubin-Lyon's. You will get in the middle, which is L4, okay? L4 third, sorry. Now, that's how, this is the argument for this thing, that the sum of the concentrations are relatively compact in L4 third, okay? Now for the step 2, we have to show that each of the concentration, not just the sums, are relatively compact in L4 third. So now you do the standard thing. We know that the sums are relatively compact, so they are strongly converging in L4 third. That means they also converge almost everywhere to some fellow, call it this one. The same is true for U2 plus U3. If you recall, in the entropy inequality, we had this estimate where there was an epsilon square sitting there. So that says that this fellow is going to 0 strongly in L1, okay? And using these three fellows, okay, I'll skip some non-trivial steps here. You can show that U1 epsilon almost everywhere converges to some fellow U1 star, okay? I mean, all this is to use Lebesgue-dominated convergence at some point. So you get almost everywhere convergence. And then you have to bound this by some LP function, right? So because the non-negativity is very crucial here. You're shown the concentrations are non-negative. So U1 epsilon, for example, is bounded from above by U1 plus U3, which is strongly converging in this one. So you can straight away use Lebesgue-dominated convergence to show that each of the concentrations are relatively compact in L4 third, okay? This is step 2. You have got the relative compactness for each of the concentrations. In the homogenization step, which I am not detailing, there will come time where you have to pass to limit in some term like this one, in an integral like this, when you are passing to the limit. We have just seen that gradient of U epsilon, U2 epsilon, for example, it's just in L4 third, okay? Because U2 epsilon was in W1 4 third. So this gradient of U2 epsilon is in L4 third, and that's the weak convergence you have. So you cannot pass to the limit in 2 weakly converging sequences, but you have just shown that this fellow is strongly compact in L4 third, but that's not good enough. You have a weakly converging sequence in L4 third, and also a strongly converging sequence in L4 third. So you have to work a little bit. And what's the conjugate of that? So that's the L4. That's why you need to get strong compactness in L4, okay? I hope you believe me. This is the term which kind of dictates you to get L4 strong compactness. Okay, this is what I'm explaining. So gradient of U2 epsilon weakly converges in L4 third. So you need U1 epsilon to at least strongly converge in L4, okay? Now, that's why, in order to use interpolation inequality, you go for higher integrability of your concentrations. Here, you use this duality estimates. I will detail the calculations here without that oscillating matrix, okay, without the oscillating matrix, and with constant DIs, but they are still different, okay? Because this computation, it appeared in a paper by Jose Canizo and some people. The reference is at the end. I forgot to write it down here. So it's a very neat argument. I wanted to show you this. But you can do a similar duality estimate even with the oscillation. Okay. So now, forget the equations for the moment that we are studying. Okay, so suppose there is a PDE equation like this, okay? Mu is a coefficient. Mu is a coefficient. It is not typically you write divergence of some coefficient times the gradient, but here it is written as Laplacian of some coefficient times the unknown, okay? So this is still a parabolic equation, so you just write like this. So there is a heat equation with initial data with 0 Neumann condition. And mu is some coefficient which is bounded away from 0 and bounded from above, okay? So you just write this adjoint or the backward problem where you just change the sign here. So you just, this is the L2 adjoint of that equation. And you put a source here, and you start with 0 at the endpoint, and you run it backwards. Now, when people say parabolic duality estimates, what they essentially say is, okay, you obtain some estimates on this fellow and use these as test functions and do estimates on U. Okay, that's the usual parabolic duality estimates. And it says the following. If you take theta to be in LQ for some Q here, then you can get supremum in time, L infinity in time, and LQ in space for the solutions to the backward problem, an estimate like this. And so using that information, using this first line, using that V as the test function in this forward problem, if you start with initial data in LP for this forward problem, for P in the other half of 2 to infinity, And then that's the duality argument. You will get that the LP estimate in time and space for W for the forward problem. Okay? Let's just keep this in mind. So this is the usual trick for the duality estimate. And you see P is greater than or equal to 2. So how do we get this L4 plus delta estimate for UI epsilons? So I'll detail the arguments when DIs are just constants. This is a very neat trick. I'll write down the same equation here, okay, with constant DIs. So there is no 1 over epsilon square term because you have used the fact that R1 plus R3 cancel, okay? It's equal to, so you get this. Then they do some crime, but it kind of works. You see, they rewrite this fellow as the Laplacian of this guy, which is exactly the same, okay? D1 gradient of U1 epsilon minus D3 plus D3 gradient of U epsilon is this fellow. Okay? They have not done much. They have explored the fact that D1s are constant, but there is another duality argument which you can use when the DIs are functions of space. But here, this is neater, so I just wanted to explain this. They'll just multiply and divide by U1 plus U3. That's what they have done. Now, what these people, Jose Canizo and co-authors, did was they defined this fellow as mu of x, mu of t of x. This is the mu. Okay? If you call this quotient as mu, and if you call the unknown u1 plus u3 as w, you are, apologies, yeah, you are in this structure, dtw minus Laplacian of mu times w, where mu, because you have got all these bounds on u1 and u3, they are bounded away from 0 and bounded from above, okay? Because it's just d1 u1 plus d3 u3 over u1 plus u3, okay? So by parabolic duality estimate, you can get whatever LP is. You need not stop at L4 plus delta. You can keep going up to infinity, okay? Not including infinity. This is the usual thing what people do when they're showing existence results for these problems, because that's how by showing uniform boundedness in L infinity, you get global in time existence for these equations. Okay. I hope you are convinced that you can get a uniform estimate in L4 plus delta for any delta positive for these concentrations. So we have done all the hard part, and this last step is just interpolation inequality, okay? So we had shown that you have strong compactness in L4 third, and we have just proved that you have uniform boundedness in L4 plus delta. You get strong compactness in L4. Okay, with this I stop by giving these references. We will post this paper very soon, maybe next week, and these are some of the references. And I welcome you to read works of Michel Pierre. There are vast literature. He has worked all through his career on reaction diffusion equations. And for example, you should read this if you want to understand how this parabolic duality arguments work. It's here. And this neat trick of writing, getting that mu just by doing that crime of multiplying and dividing by u1 plus u3 was done by these people, Canizo, Laurent de Villette, and Clemens Fellner. Yeah? Okay, then there are these things of bootstrap arguments, and yeah, this I have not understood myself, but if you can understand the GeoGebra approach for these problems, you can read Thierry Goudon and Alexis Wasser's results. Okay? Okay, thanks.